today we will look at how receptors can be targets for new drug development. So, just to recall, we have looked at receptors, how they function and so on, and typically there is a messenger which comes and binds to the receptor, and after the receptor binds to the messenger, there is an induced fit which results in amplification of the signal. And so, here is the example of a G protein coupled receptor which we have looked at previously. And of course, we also are very well aware that such communication is vital for the normal functioning of the body. So, what goes wrong is that either there is a increased functioning of a receptor or diminished functioning of a receptor, and so this leads to a large number of ailments such as depression, schizophrenia, heart problems, muscle fatigue, and just to name a few. So, what could go wrong? Okay. So, one problem is that if there are too many chemical messengers which were released, and so then the sort of target cell starts to overheat. Alternatively, if there are too few messengers that were sent out, then the cell becomes sluggish, and so we do not respond as well to stimuli. So, both these are actually problematic, and so our approaches towards solving these problems would be opposite. That is, we would want to decrease the number of chemical messengers in the first case, whereas we would want to increase the receptor function by using or signaling by the second case. So, it is at this point that drugs can play a vital role, either by acting as replacement messengers or by blocking receptors from receiving their natural messengers. So, let us look at the first case now. Here what we would introduce this term known as agonists. Agonists are nothing but small molecules which mimic the natural messenger and activate the receptors as the natural messenger would do. Okay. So, here is the a cartoon that represents it. So, here let us say you have before a drug treatment, there is some receptor that is being activated by this ligand, and after the receptor is activated, there is normal cellular activity. But now, let us say we want to augment this cellular activity, then we would add what is known as an agonist drug, which would then go and bind to this receptor, and since there are more number of these molecules, the function of the receptor would or the cellular activity would enhance. Okay. In contrast, the drugs that block these receptors are known as antagonists. So, antagonists basically what they do is that if there is on the on this side, you see that before drug there is some functioning of a cell that is happening, and now in the presence of an antagonist, the antagonist would go and bind to the receptor, but will not activate it. That means that the signal is not going to be transmitted. So, therefore, an antagonist would bind to the receptor, but it would not activate it, and therefore, the natural messenger will not have a place for it to bind. And so, together what this results is a diminished cellular activity. Okay. So, what determines whether a drug acts as an agonist or an antagonist? Is it possible to predict whether a new drug will be one or the other? So, these are some of the important questions that we would ask in this lecture, and in order to answer this, what we need to do is we need to go into a fundamental molecular level and consider what happens when a small molecule binds to the receptor. Okay. So, we have looked at previously in detail a broad picture we have looked at as to how various classes of receptors function, but we have not really looked at it from the molecular level. So, what we will do now is to look at these types of interactions and see how we can design an antagonist or an agonist as the case may be or as the application may be. Okay. So, just to recall, the understanding of how a receptor functions is that there is what is known as an induced fit. So, there is a natural messenger which then comes in, binds to the receptor, and the receptor would have to alter its shape in order to bind to this messenger molecule, and the messenger molecule would also have some shape changing effect, and together it binds, and then that results in a message being sent out. After the message is sent out, we will look at how receptors are regulated later, but then the messenger must dissociate and then the signal transduction stops. So, together this induced fit model helps us understand how signals are transmitted by binding of a messenger to a receptor. In order to design an agonist, we need to know what the binding sites are. Okay. So, we would have to have the knowledge as to where the receptor binds the ligand, how it binds it, and then it would help us understand what is going on in or how the receptor functions. So, keeping this in mind, there are three major characteristics that or major requirements that we would need in order to design an agonist. The first one, the drug must have the correct binding groups. Okay. So, if it does not have the correct binding groups, then it is likely that it may not bind to the major parts of the receptor. The second one is a drug must have these binding groups correctly positioned. So, not only must it have the binding groups, but they must also be correctly positioned. And lastly, there must be the right size for the binding site. So, if we design a molecule which is too large, then it may not even go and interact with the receptor site, and therefore, it may not be able to present its binding groups in the proper manner. So, now let us look at what the binding groups are. Okay. So, let us say we have a receptor, a hypothetical receptor, and we know the structure of the natural chemical messenger. So, as shown here, this is the hypothetical neurotransmitter. Now, what we need to do is to understand this molecule from the perspective of how it is going to bind to the receptor. So, looking at this group, we should be able to reasonably predict what happens in this molecule and what are the major binding groups that are important. Okay. So, let us say we look at the receptor site, okay, receptor binding site, and again, being a hypothetical example, we could suggest that there could be three major interactions. So, the first interaction is this hydrophobic interaction or van der Waals interaction over here. The second one would be hydrogen bonding, and the third one would be an ionic bond. Okay. So, we can reasonably predict that these may be the three major interactions that would occur with this hypothetical neurotransmitter. So, based on this information, we could then design a series of compounds which have similar functional groups. So, starting from here, let us say what we do here is we replace the hydroxyl group with an amine. So, the amine has a hydrogen which can interact in hydrogen bonding. So, therefore, it may be a good replacement for a hydroxyl group. Alternatively, we could close this ring. So, if you see here, this is an open chain compound, and we can close this ring and make it into a 5-membered pyrrolidine. Okay. Alternatively, we could replace this benzene ring over here with an olefin. So, all these have some small tweaks in the functional group, and then what we could reasonably suggest is that these may be compounds that may go and bind to this receptor. Okay. So, there could also be situations where we could reduce one of the interactions. So, let us say we design this kind of a molecule where you have a lower van der Waals interaction, or here where there is no hydrogen bonding capability. So, what ends up happening is that you will have lesser number of interactions with the receptor. So, it would we would predict that it would have weaker binding. Of course, here in this process we are actually making an assumption. We are assuming that all three binding groups are essential. Okay. So, it may turn out that the van der Waals interaction may first occur, and that may have a major impact on altering the shape of the receptor, and with ionic bonding and van der Waals interactions alone, it is possible that the receptor can function exactly the same way as it would even without the hydrogen bonding interaction. So, what we would need to do, as you will figure out, the logic that we are trying to apply here is that we would first start out by trying to predict what the binding interactions would be, and then from there we would probably systematically change the group so that we can understand which binding interactions are more important and which binding interactions are not that important. Okay. So, and this is the exercise that we would normally undertake if we want to design a agonist, right. And as we can see here, there must be a balance. So, if the binding interactions are too strong, then it is possible that it is going to bind, but it is not going to let go. Okay? And if that happens, then that is not very desirable. Alternatively, it is also possible that you will have a very weak binding, so that then the conformational change that is required to occur may not happen. And so, the balance that needs to be achieved is very important. Okay? So, if the interactions are too strong, then it is possible that it will not leave and it will not return to its original shape. So, we will have to figure out what is the optimal number of interactions for us to mimic the natural substrate. Okay. Secondly, we need to look at the position of the binding groups. So, here we would if for example, we design this molecule which has an extra CH2 here compared to the natural messenger, then what we have done is we have sort of displaced the hydroxyl group over here, whereas by keeping the rest of the structure the same, it is likely that the other two interactions will not be affected as much. Now, it is possible that because we have displaced or we have moved this hydrogen bond a little bit towards the right, or hydrogen bonding group towards the right, it is possible that you may not have any interaction with the receptor hydroxyl group, which would sort of cut one of the hydrogen bonding interaction. So, therefore, the position of the binding group is very important in how we design the agonist. The next part is chirality. Okay. So, we will look at some of the aspects of chirality later in this lecture, but suffice to say now that the mirror image of the neurotransmitter may or may not bind to the receptor surface. It is possible that the mirror image may not have the same level of interactions as the original molecule. So, although the structure has the same formula and the same constitutional structure as our original structure, and we will look at later, it will have the same physical properties and will of course undergo the same chemical reactions, but it cannot interact with all the binding regions of the receptor at the same time in the same level. So, therefore, even chiral or the mirror image molecules may not have the appropriate binding regions. Okay. Now, let us take a minute and try to understand what chirality is. I am going to put this picture out here and just take a look at it, and then we will come back to this later. Okay. So, the classic example of why chirality is important in drug discovery comes from this drug called as thalidomide. Okay. You will see here this person Thomas Quasthoff, who has won the prestigious Grammy Award, and he was one of the victims of a drug that has been taken for in an incorrect manner. So, as you can see, his hands are less developed and they are extremely small. So, one enantiomer of this drug was used for was able to help with morning sickness during pregnancy, whereas the other enantiomer caused abnormalities in the growing fetus, and at that time people were given this as a racemic mixture. So, this is a classic example of how chirality is very important in drug discovery. So, in order to understand chirality, first let us start with nomenclature. Okay. So, here is a structure of natural alanine, and so we will look at the Kahn-Ingold-Prelog nomenclature priorities, and let us assign the priority based on that. I am not going to go over the CIP rules because that is taught in basic organic chemistry, but if we were to assign priority, so then this NH would be number 1, COOH would be 2, methyl would be 3, and hydrogen would be 4. And so, what we would do is we would rotate so that the hydrogen points into the paper. And so, now if I were to assign the priority, I go from here to here, and this would be S. Okay. Now, if I were to because if you are not moving in a clockwise manner, it is S, and if it is a clockwise manner, it is R. This is the structure of S-alanine. Now, let us take a minute and look at how we would assign the R and S lactic acid. Okay. So, here you would have figured out by now that the structure over here is R lactic acid, and so it can also be represented without the hydrogen in the following manner. Now, if we were to take a bottle of the R enantiomer and a bottle of the S enantiomer, one of the features that is really different is the way in which the molecule is able to interact with plane polarized light. So, in order to study this, we would use what is known as a polarimeter. So, here is a polarimeter cell in which we could put in the solution of the substance, and it would be exposed to a sodium lamp, and then there is a polarizer that would make it into a plane polarized light, and then of course, there is a detector. So, if there is no rotation, then what happens is that there would be 0 degrees, there is no rotation from either right or left. But if the constituent of the solution is able to rotate the plane polarized light, you will see that there is no signal at this angle, but once you move it to a slightly different angle, then you will see some signal. So, what this means is that this molecule rotates the plane of plane polarized light, and one can measure this angle, and we would be able to determine the number, and this will help us understand whether it is dextrorotatory or levorotatory. So, using this technique, one can distinguish between the R and S isomer, and please keep in mind there is no connection between R and dextrorotatory or S and dextrorotatory. Either one of them can rotate the plane of plane polarized light in any way. The only thing that is absolutely right is that R will rotate it in one direction and S will rotate it in the opposite direction. Okay. Now, let us look at the concept of diastereomers. Diastereomers are stereoisomers which do not have a mirror image relationship. So, the example here is fumaric acid and malic acid. As you can see, they have the same connectivity, that is, they have 2 carboxylic acids and then they have an olefin, but in space they have differences. So, this the fumaric acid is trans to the 2 carboxylic acids are trans to one another, whereas in malic acid they are cis to one another. So, this difference between trans and cis manifests itself in a number of physical and chemical properties. So, here for example, the melting point of fumaric acid is between 299 and 300 degrees centigrade, whereas for malic acid it is 140 to 142 degrees centigrade. So, diastereomers have a number of, although the connectivity is identical, diastereomers have a number of differences in their physical and chemical properties. So, here is another example where you have a cyclohexane system, and so here you can draw this out in the chair conformation at your leisure, but this is the cis isomer over here and here is the trans isomer. So, the groups that we are looking at are the tertiary butyl group and the hydroxyl group over here, and the melting point of the cis isomer is about 82 to 83 degrees centigrade, and the trans isomer is fairly close, but there is a difference, but it is close. The melting point is 80 to 81 degrees centigrade. However, if we record the proton NMR spectrum of the cis isomer and the proton NMR of the trans isomer, the differences become quite significant. So, using NMR techniques, one can actually distinguish between cis and trans isomers. However, in the case of chiral compounds, that is in the case of R or S, the NMR spectrum would look identical. Okay. So, what we will do now is to look at this epoxide and try to understand how this epoxide, the various stereoisomers that are presented. So, what we need to do is we look at these 2 structures and we need to identify whether there is any plane of symmetry in these molecule or any element of symmetry in this molecule. So, the structures on the top have no plane of symmetry, and so they must be chiral. Okay. And now, we can draw a mirror plane and look at the mirror image of these molecules, and these 2 structures are also non superimposable on the original structures, and therefore, these molecules are enantiomers of each other. And now, if you just want to check it, you can just do a rotation and just make sure that they are not superimposable. Now, the task is to assign R or S nomenclature to these molecules. So, you must have done it by now, and so the answer is S over here and R over here, and the enantiomer of this molecule has R and S in the of the corresponding carbons, and similarly the enantiomers of the other two molecules are shown over here. But this group of molecules has a diastereomeric relationship with the other group of molecules. So, as just to recall, diastereomers are molecules which do not have a mirror image relationship. So, therefore, there is no mirror image relationship between this set of molecules and this set of molecules. Okay. So, let us look at this example of ephedrine and pseudoephedrine. So, ephedrine has if you are assigning R and S stereoisomers, there are two isomers here, R and S. The carbon here is R and the carbon here is S, and pseudoephedrine has S and S. Okay. So, between the two isomers, between the two enantiomers of ephedrine, there is no difference in the melting point. So, they both are 40 to 40.5 degrees centigrade, and as we discussed earlier, the specific rotation of this one enantiomer is opposite to the other one. So, here it is minus 6.3 and plus 6.3 as we would have expected. In the case of pseudoephedrine, the melting points are again identical, 117 to 118 degrees centigrade, and the rotations are exactly opposite, that is, one is minus 52 and the other one is plus 52. Okay. You can take a few minutes and figure out the nomenclature of these molecules, and that would be a good exercise for you. Now, there is another important nomenclature that comes in stereochemistry, that is called as syn and anti. If we were to look at a molecule, put it draw it in a plane, and let us say we are this hydroxyl group is pointing towards us, and this other hydroxyl group is pointing again towards us, and this kind of molecule would be called syn, that is SYN. Okay. And if the corresponding diastereomer of this molecule, where the hydroxyl group is pointing, one hydroxyl group is pointing towards us and the other hydroxyl group is pointing away from us, this molecule would be called as anti. Okay. So, the syn compounds are actually enantiomers of each other, and the anti compounds are enantiomers of each other. However, these two groups, syn and anti, are actually diastereomers of each other. Now, there is a small catch. The once I use this molecule which has the absolute stereochemistry RS, and then if I rotate the right hand side of the molecule like this, okay, I end up with a compound which is shown here. So, this molecule is a special molecule because it has a mirror plane of symmetry. So, if I have to draw a plane of symmetry right between this exactly in the center of this bond, then one side of the molecule is identical to the other side. So, the condition for a compound to be chiral is that it must have no elements of symmetry. So, this molecule, although it has an R and an S, has an internal plane of symmetry, and therefore, this molecule turns out to be achiral. And you would find that this molecule has no interaction with the plane polarized light, and so the value is 0. Whereas, the corresponding tartaric acids, plus tartaric acid and minus tartaric acid, very nicely give a rotation of 12 degrees, and of course, as we would expect, their melting points are identical. So, this achiral diastereomer is called meso. Okay. So, tartaric acid, whose structure is shown above, has two enantiomers and one meso molecule, okay, and that is achiral. And therefore, hopefully, in this exercise you have found that there can be compounds that are chiral, and the molecules which are chiral are going to rotate the plane of plane polarized light, and this plane polarized light rotation is going to be opposite to one another. However, when there is more than one stereocenter that is present, it is possible that in certain cases you will have some additional element of symmetry which was not present in the original molecule, and once this additional element of symmetry presents itself, then the molecule becomes achiral. Okay. So, I will leave you with these structures, and we can look at assign the stereochemistry of these molecules. Okay. Now, since we have figured out that dealing with with a single enantiomer is what we would like to do, we need to be able to figure out asymmetric synthesis. That means, we need to be able to figure out how to make molecules as a single enantiomer. Okay. But if that is a separate topic, but what normally happens is that we will end up with a racemic mixture. So, consider this molecule, this alcohol here, and this alcohol is chiral, and you will find that it is, when we, let us say we do a reduction of the ketone to give you the alcohol, you will end up with a racemic mixture. One way in which we can actually separate out the two enantiomers is by converting this molecule or this racemic mixture into the corresponding diastereomer. As we have discussed earlier, diastereomers have very different chemical and physical properties, or can have very different chemical and physical properties, and therefore, they are actually separable by simple chromatography techniques. So, what we would do, the strategy that we would adopt is to be to carry out a synthesis where we can make a pair of diastereomers. So, here is the acid that we would use, and this acid is present as a single enantiomer, and now, so once it interacts with the racemic alcohol, it would form an ester, and this ester would have again 50% of the R and 50% of the S, but since this chiral center is there is a single chiral center here, you would end up with a mixture of diastereomers. Okay. And now, we can separate out the diastereomers, and once we separate it out, then we will be able to use the one of the enantiomers for further transformations. Okay. Now, after we separate this out, we could then hydrolyze off this ester, and we would have with us two enantiomers which are separated, and this molecule that we used to make the diastereomer can be recovered and recycled. So, naproxen and ibuprofen are actually two molecules which are very commonly used as non-steroidal anti-inflammatory drugs or painkillers. And so, naproxen and ibuprofen, they both are chiral, okay, and the chiral center is present over here. Okay. Now, ibuprofen is sold as a racemic mixture, and it anyway racemizes inside the body, whereas naproxen, only the S enantiomer of naproxen has anti-inflammatory activity. So, in order to resolve the naproxen, what we would need to do is we do what is known as crystallization. So, crystallization is a process by which we can use enantiomerically pure molecule to co-crystallize with the desired compound, let us say a racemic mixture, and some again, because we are introducing a diastereomeric environment, it is possible that one of these enantiomers actually crystallizes out, while the other one remains in the solution. So, by doing this, what we do is that we set up a crystallization reaction, a crystallization setup, and this allows us to discriminate between the two enantiomers. Again, it is not necessary that all the enantiomers are going to crystallize out separately, but it is a commonly used methodology to be able to separate out one enantiomer from the other, and it works very well in the case of naproxen. Okay. So, once the molecule crystallizes, then what you can do is just filter it off, and then we need to convert it to the sodium salt, which can be done with sodium hydroxide. And now, the glucosamine that is used is now recycled. Okay. Another important technique by which we can separate out enantiomers is chiral chromatography. So, chromatography typically is carried out with silica, and silica surface absorbs the molecule, and it is able to, because the molecule has some elements of polarity in it, it would bind to the silica surface. And once we elute out the silica surface, it is possible that the compound that is binding stronger will elute slower, while the molecule that binds weaker would elute faster. So, this is a very commonly used technique to separate out molecules in organic chemistry, but since enantiomers have identical physical and chemical properties, most physical and chemical properties are identical, silica gel will not be useful for separating out enantiomers. However, using the same concept that we looked at before, we can convert these enantiomers into diastereomers, and now since diastereomers may have different physical and chemical properties, one would be able to separate this out by chromatography, right. Alternatively, the surface of the silica can actually be derivatized and you can make it chiral. So, that is what is done over here. If you introduce a chiral molecule on the surface of silica, now what happens is that you can separate out these molecules because you are introducing a diastereomeric environment. So, here is an example of this molecule which is an analog of Valium. So, the R enantiomer and S enantiomer need to be separated out. So, what we would do is we would take this column, we will have a chiral stationary phase, and once we load on the racemic mixture to the column, what happens is that they both will go and bind to the surface of the chiral stationary phase. Then we elute it out, and since the S isomer binds stronger to the environment, that means that the diastereomeric environment that is created seems to have a stronger binding for the S isomer over the R isomer, and so there is a gap between the S and R isomer in terms of how they elute. So, the R isomer elutes faster and reaches the bottom of the column first. So, once we collect this portion and we keep it separately, and then we start collecting the fractions where the S isomer presents itself, and then the S isomer can be separated out. So, again this is a very powerful technique to be able to separate enantiomers. Of course, ideally we would like to synthesize molecules which are of single enantiomers, and that is the field of asymmetric synthesis that has emerged to be able to do that. So, the way they do it is to be introduce similarly a diastereomeric environment either in the as an intermediate or in the transition state, and that enables selective synthesis of only one enantiomer over the other. Now, coming back to the original picture that we looked at, this picture actually has two left hands. So, how do we understand chirality, or what is the importance of chirality in medicinal chemistry? So, pharmaceutical agents are usually synthesized from simple starting materials, because you need to be able to scale it up to kilograms and tons and so on. And so, they usually use achiral chemical reagents. Okay. So, these achiral chemical reagents, as we looked at earlier, are incapable of distinguish between two mirror images of a chiral compound. So, as a result, most chiral drugs are synthesized as a mixture, but we looked at previously some problems with this approach, because one enantiomer could be quite toxic to or could have very bad effects on the human, whereas the other one is going to actually help. So, this also the way in which this is going to interact with a target receptor, for example, is going to be different. So, even if the wrong enantiomer does not do any harm, it is a great waste of time, money and effort to synthesize only 50% efficiency. So, this is one of the biggest areas, as I mentioned earlier, where you have to selectively synthesize a single enantiomer of a chiral compound. Now, let us take a little bit of time and look at what a pharmacophore is. So, what we have looked at earlier is that there has to be a binding center in the receptor, and the molecule that we are using or we are designing must go and bind to this area. Okay. So, the importance of having binding groups in the correct position helps us to design drugs based on what is considered to be important pharmacophore of the messenger molecule. So, pharmacophore is basically the concept where we have the important parts of the binding groups which for the messenger molecule which we use. Okay. So, here of course, the assumption is that the correct positioning of the binding groups is what decides whether the drug will act as a messenger or not. So, it is possible that the rest of the molecule serves only as a scaffold to hold these groups in position. So, these are some assumptions that we need to make. So, therefore, the activity of apparently disparate or very different structures at a receptor can be explained if they all contain the correct binding groups at the correct position. So, as I mentioned earlier, it is possible that a receptor can interact with molecules which are completely different in structure. Now, our job is to be able to identify the correct binding groups and figure out if they are at the correct positions. and that is how we can actually design completely novel structures or molecular frameworks which can bind to this receptor, and this would lead to a new series of drugs. So, let us look at the concept of size and shape. Okay. So, it is possible for a compound to have the correct binding groups in the correct position and yet fail to interact effectively because it has the wrong size or shape. So, in this example, this is a group, methyl group, which is meta to the functional group over here, and that what it can do is that when it enters the receptor surface, since there is a induced fit going on here, it is possible that the binding site repels and this does not go happen. Okay. Second thing, we also have a propyl chain on the amine. Since this amine has a propyl chain, it is possible that this carboxylate is sterically hindered from interacting with the amine. So, therefore, not only does it have to have the correct binding groups, but it also must have the correct size and shape. So, of course, there is a level of flexibility in the binding site, and a potential agonist that we have designed may be looking too large, but a slightly different induced fit might occur, which allows the molecule to fit and bind and still activate the receptor. So, therefore, it is a fairly complicated situation, but yet we need to understand certain key aspects of this functioning, and clearly size and shape are important. Some of the other design strategies that people employ is that since the receptor is a protein, there are a number of other binding regions which may play an important role. Okay. Since we are basing our understanding on the natural messenger, it is possible that we may be ignoring some other binding sites. So, these binding interactions may be exploited in designing new molecules. Okay. Now, much like the allosteric center and enzyme catalysis which we have looked at earlier, there are also allosteric modulators. So, some drugs have an indirect agonist effect by acting as an allosteric modulator. So, by binding at an allosteric site on a target receptor, what they do is that they mimic the action of the endogenous modulator and enhance the action of natural or endogenous chemical messenger.